lecture of the course, and therefore I would start right away. Maybe I will need extra 5 minutes, I don't know, depends on how much we are going to do. So my question to you, what do you know about phase transition theory?
We know first order and second order phase transition.
But do you know what Landau theory is?
No, not that much.
Because I am going to proceed beyond Landau theory, well, which assumes that some basic knowledge of Landau theory should already be there. Okay, lecture number 10. This is superconductivity part 2. And in particular, Ginzburg-Landau equations. Sorry, this is going to be a really tough lecture. It continues our phenomenological approach. So Monday, we discussed several important things. First of all, we discussed that certain metals become superconducting at temperatures below Tc, and behavior of the thermodynamics, namely we briefly discussed specific heat, supports the statement that this is second order phase transition. Namely, there is other parameter which we identified similarly to interacting Bose-gas as a wave function of condensate. So there is a superfluid component which appears, and this other parameter well, it's going to be complex pattern, therefore let me write modulus, continuously changes as a function of temperature and continuously becomes zero at critical temperature Tc. As a result, the specific heat experimentally demonstrate a jump at the same critical temperature. So I briefly told you that according to Landau-Ehrenfest classification, the order of derivative of thermodynamic potential coincides with the order of phase transition. So to say, the specific heat is the second derivative of thermodynamic potential, therefore discontinuity of the second derivative tells us that this is second order. If you look at liquid gas, liquid vapor transition when you boil your water in the morning for tea or coffee, you see that the specific heat becomes infinite because you bring some energy into the system, you heat it, but the temperature doesn't change. The temperature is at the boiling temperature. Therefore, specific heat is equal to infinity, and entropy has a jump. Here entropy is continuous but has kink. So for the first order phase transition, which is, for example, liquid vapor transition, the first derivative, which is entropy, has a jump, and therefore this is the first order phase transition. Okay, before I come to Ginzburg-Landau equations, let me recapitulate how basics of theory of second order phase transition can be constructed. From now on, we are dealing with second order phase transition because we are discussing superconductivity. So Landau suggested that take some thermodynamic potential, which could be energy, Gibbs energy, Helmholtz energy, depends on the conditions, which I don't like this chalk. It produces terrible noise. in the proper variables. Proper variables could be pressure, for example, and temperature. Because pressure guarantees you mechanical stability, temperature guarantees you thermodynamical stability. I will forget for a while about second variable and assume that this thermodynamical potential, say this is free energy, depends on temperature. So the thermodynamic potential is extensive variable, so it should be proportional to the water. So without losing any generality, I'm going to deal with the description of it at the vicinity of phase transition point. I can Taylor expand. So the free energy is analytic function of the order parameter. I can Taylor expand, and since I'm expanding around the minimum, so it's some constant plus coefficient A times psi modulus square plus coefficient B over half psi modulus 4, and for proper dimension let me multiply it by the volume, because thermodynamic potentials are extensive variables, should be proportional to the volumes. So A and B are some coefficients, and psi is the order parameter. So why it is like that? So what we see, that if we are above the phase transition point, T is larger than Tc, then the free energy phi minus pi node as a function of modulus psi behaves quadratically and vertically. So the stable minimum corresponds to zero order parameter. So here psi is equal to 0. However, if we assume that coefficient Ra changes at the phase transition point, we will write that A is equal to another coefficient alpha times tau, and we introduce dimensionless variable tau, which is T minus Tc over Tc. This guarantees us that for temperature larger than Tc, A is positive, and therefore the dependence of free energy of the order parameter is polynomial with quadratic dependence at the origin. However, if we now assume that below Tc the coefficient A becomes negative, then the free energy depends on temperature. That way we will see it. So there is non-trivial minimum appearing at some point corresponding to non-zero value of psi. Let's find this minimum. In order to do this, psi is complex order parameter. We said that this is a wave function of a Cooper pair. We discussed Monday that because of interaction of electrons with the lattice vibrations, pairing of two electrons is possible in the vicinity of Fermi surface, right? So therefore, we say that the wave function is order parameter, the wave is a complex object. Therefore, with a complex object, I have two linear independent variables. For example, I can take real part and imaginary part are two linear independent variables. However, instead of doing that, I can take psi and psi complex conjugated as two independent variables, because this is a linear combination of real and imaginary part with sign plus I and with sign minus I. So, in order to find a minimum, I will take a derivative of the free energy, which is a function of psi, with respect to psi star, and say that d phi over d psi star, and say that this should be 0. This is a condition for extremum of the free energy. So this condition, this is psi times psi star, this is psi times psi star squared. So what I have is A divided by psi plus B divided psi modulus square psi is equal to 0. So this equation, which I can take psi out, A plus B psi modulus square equal to 0, obviously has two solutions. First solution is psi equal to 0. This solution is realized at temperature bigger than Tc. However, below Tc, there is yet another root of this equation, namely psi modulus square is equal to minus E A divided by B. You see that if A is negative, this is a positive quantity, and therefore below Tc we get psi modulus is equal to square root over modulus A divided by B. Let me call it psi naught. Let us see that this root corresponds to the minimum of free energy. So let me take it at psi naught. So this is equal to phi naught minus modulus A times modulus A over B. So B doesn't depend on temperature. This is a positively defined constant which guarantees the stability, that free energy grows up. Plus B over 2 A over B square. So we do have phi naught. So this is minus A square over B. This is plus A square over 2B. So this is minus modulus A square over 2B. So this is this value. We do say, and probably you will have your course of advanced quantum statistics, whatever, later, but please look at the textbook. I cannot say more about second order phase transition from the point of view of Landau function right now, but I will be dealing now with Landau functional instead, and which is generalization of that. What I suggest you to do, take this theory and compute the specific heat and see that indeed this theory provides a basis to explain the jump of specific heat, and you can express it in terms of the constants A and B at Tc. This is exercise, please do it. Where this theory is valid, as I said, we do Taylor expansion. So therefore we assume that these terms are small. Smallness of these terms tells us that we are in the vicinity of the phase transition point. Otherwise the order parameter is large. Therefore the theory is valid only if tau, and I will say modulus tau, because I'm going to derive equations valid both below Tc and above Tc, should be smaller than 1. Tau is dimensionless parameter. In principle, it's not all. On a tutorial, which I think Jean-Paul Fayet will discuss with you, you will also see that there is a low bound. So tau should not be sufficiently small. Otherwise, there will be critical fluctuations. Did you discuss with Professor Nersisian critical fluctuations? Yeah. So, tau, what you should know today is that tau is bounded from above by 1, and it's bounded from below. However, this bound from below, which for superconductor, well, for second order phase transition is known as a Ginzburg number, for superconductors is of the order of 10 to the minus 12. So we would not care about that. So basically, this nearest vicinity of the phase transition where the critical fluctuations become important, and the theory which I'm going to derived for you today becomes unvalid is so small that in real nowadays experiments for conventional superconductors, one should not care about these critical fluctuations. For magnets, it's different. So the same kind of theory we will then apply for magnets, and I come back to this. We discuss so-called Einstein-Cernicke theory, but later on. So today, this is domain of validity. Well, let me say this is Ginzburg number, and this is 10 to the power minus 12. Forget about it. Okay. Are you okay with that? Good. So, on Monday, we discussed phenomenology based on London equations. So we derive equation for the supercurrent based on gauge invariancy. But now, I would like to demonstrate you the tool, the standard method to derive this equation from the same ground as the simple possible theory which I just introduced you. So, what I will do? I will do the following. I will assume now that the free energy is a functional of the order parameter. Do you know what the functional is? Do you know what the variational derivative is? Does everybody know? Because I'm going to be slow. I will compute variational derivatives. In principle, I could do the same when we derived the Gross-Pitayevsky equation, nonlinear Schrödinger equation. Instead of computing commutators, I can put it in the action and take functional derivatives. But I didn't do that because I prefer to do functional derivatives right away, right now. So, the set free energy now is a function of psi. Psi is a complex order parameter. So what I assume, so what was assumed in the Landau theory? That the order parameter is uniform in the system and doesn't vary from point to point in your superconductors. This is strong but very efficient assumption. However, in real superconductors, of course, the wave function can slowly depend on a coordinate. We will see that it depends on a coordinate on a scale which we'll then associate with coherence length. We will estimate this coherence length. But since I just erased it, there is a volume, so I will say that this is Fahrenheit node. And instead of writing something proportional to the volume, I will write the integral over dr. And now I will do pretty the same. I will write that this is A psi modulus square plus B half psi to the 4. Well, if psi is uniform, we just have the volume in front. However, this is not all. I will now write a term which depends on gradients. So to say, I will write down the kinetic energy. So we agreed and we understood that the order parameter associated with the Cooper pair. So therefore, the kinetic energy is 2 over mass. Mass of the Cooper pair is twice mass of the electron. So this is 2m. And here I will write minus I h nabla. I want to consider electrodynamics and magnetoelectrodynamics of superconductors. Therefore, from very beginning, I will take into account that there is a magnetic field. Therefore, this is a momentum. In magnetic field, I have to take a long derivative. Therefore, I will write minus the charge of Cooper pair is 2e over c, vector potential A times psi modulus square. This is kinetic energy. And I need to write, I add magnetic field. I need to write the term depending on magnetic field to the, so b square over 8 pi, where B is nabla. You see that this is direct generalization of Landau function to the Landau functional. So psi depends on R, of course. And again, I assume that at temperatures above Tc, A is positive, and that at temperatures below Tc, A is negative. Therefore, A is alpha times tau. And tau is T minus Tc over Tc. The order parameter changes continuously. For the first order phase transitions, as we will see later, the order parameter jumps. So therefore there is discontinuity. If there is a discontinuity, one cannot Taylor expand. Good. So now I do pretty the same what I did for Landau function, except I'll take into account that this is functional, and therefore I will take functional derivative. Psi is a function. The object which depends on functions or a function is called functional. So therefore, what I will do, I will allow psi star to replace it by psi star plus delta psi star, and compute the coefficient in front of delta psi star, and find the new equation for the order parameter. This would be first Ginzburg-Landau equation. I'm going to derive it. Then I will assume that the vector potential can also vary. So I will write delta A, and by varying, here is the delta phi over delta psi star is equal to 0. Here delta phi over delta A is equal to 0. I will get second Ginzburg-Landau equation. Why do I need this equation? Because these equations, which as you will see, system of nonlinear equations, will provide me the basis for computing thermodynamical and electrodynamical properties. And it appeared that the theory which I'm going to derive in front of you today, which was suggested by Ginzburg-Landau in 1950, became extremely powerful tool for description of properties of superconductors. Well, in principle, it can be extended for magnetic system, for whatever, even for coexisting phase. And in 2003, Ginzburg got a Nobel Prize precisely for that. Landau got Nobel Prize before, I think in 1962, but this was for Fermi liquid theory, which we also had a chance to discuss. Okay, the lecture is going to be tough because I'm going to be slow, and let's start calculations. Okay, number one. Psi modulus square is psi star times psi. Psi and psi star are two independent variables. Therefore, when I do this replacement, I have a psi times psi star plus delta psi star, and this is equal to psi modulus square plus psi star delta psi star. Okay? This is how the variation of this term appears. Second, psi modulus 4. This is psi star psi square. So, this is psi modulus square plus psi delta psi star square. I use this fact. So this is then terrible quantity of chalk. Psi modulus 4 plus 2 times psi modulus square psi delta psi star plus term of the order of delta psi star square, which I drop because I need to take this variation in the limit delta psi goes to 0, delta psi goes to 0, and therefore this term will disappear. So I will keep only linear in delta psi star terms. What remains is to compute the variation of this term. So this is 1 over 4m minus I h nabla minus 2e over ca psi times I h nabla minus 2e over ca psi star. So now I replace psi by delta psi. 1 over 4 m minus I h nabla minus 2e over ca psi I h nabla minus 2e over ca psi star plus delta psi star. So the first term will give me 1 over 4m modulus minus I h nabla minus 2e over ca psi square. In addition, I have this term plus 1 over 4m minus I h nabla minus 2e over ca psi I h nabla minus 2e over ca delta psi star. So now I should recall that there is integral over dr. So let's forget about this term because I'm computing delta f. So this is delta f. So I need to write down 1 over 4m integral over dr minus I h nabla minus 2e over ca psi I h nabla minus 2e over ca delta psi star. First of all, I should remember that I use a certain gauge. I will use a gauge delta times A is equal to 0. So I would like to transfer this integral as a divergence of some function plus something. Therefore, I will write it down as 1 over 4m integral over dr. First of all, let me take a divergence of delta psi. I will write it as I h times minus I h nabla minus 2e over ca psi. This is scalar product. But since I add something, I should also subtract. So I should subtract term which would be minus 1 over 4m integral over dr and So this is this term. So therefore, I should subtract the gradient acting on this part and A. So this is then I will write it I. So I will subtract term with the gradient. So this is then minus I H nabla. I have this term which remains intact, 2A B over C. And since it acts twice, square. So this is plus over psi m times delta psi star. Okay? So, what I did, I took this term, this is gradient of delta psi star. I wrote expression where gradient acts on both. So, if I take the gradient of this, it will be gradient on a delta psi star times this plus this times gradient to this. And I need to subtract it. This is how I did it. Okay? So, now I have a term which is divergence of something. I may use the Gauss theory, which tells me that the integral over dr divergence of some vector k can be written down as the surface integral ds over k. This is Gauss theory. Okay? Let me see that I didn't make a mistake with a sign. No, I didn't. So therefore, what remains here is a surface integral. So let me put number 4 here, and just for integral number 4, I will write down that this is surface integral over ds, and I have this expression delta psi star. So this is I h over 4 m minus I h nabla minus 2e over c a psi. So I have this, I have this, I have this, and remaining thing is that. So delta psi star, actually, these two terms, namely combination of this, and this, and surface term are the volume and surface term. Therefore, when I vary over delta psi star, I should put them equal to 0 independently for arbitrary delta psi. Because this is a vector, this is a scalar. So each of these terms, namely this and the rest, should be equal to 0 independently, because delta psi star is variational parameter, it's arbitrary. Okay, therefore, I arrive to the first Ginzburg-Landau equation and a boundary condition to it. So, the first equation says that A times psi plus B over 2 times 2 psi star, psi module square psi. B psi plus 1 over 4 m minus I nabla h minus 2e over c a square psi is equal to 0. This is the same kinetic energy, p square over m. Yeah. So this is equation number 1. You see, this is nonlinear differential equation, which in a sense resembles what we discussed with the gross-Bethe test. Okay? But I have a boundary condition which tells the arbitrary psi. So there is a surface. There is a normal to this surface. The boundary condition reads that n, the normal, times minus IH nabla minus 2E over C A psi should be equal to 0. We don't have time to discuss the significance and importance of this boundary condition. I should mention that actually this boundary condition is applied for the contact between superconductor and dielectric. In principle, what we consider that outside superconductor is vacuum. However, this is important boundary condition which should be accompanied with a Ginzburg-Landau equation. So the difference between the equation in the Landau theory, which we just discussed before, and this equation in this term. You see that first two terms just reproduce the previous equation when I assume that the order parameter is uniform and doesn't depend on R. The only difference now is that we do assume that the order parameter can vary from point to point, so therefore we have a gradient term. Okay? Good. So now, I should proceed with the derivation of second Ginzburg-Landau equation. Is it clear what I'm doing?
I'm sorry, can you clarify again why we separate the volume term and the surface term?
They are of different symmetry. One is scalar, another one is vector. They are of completely different origin and different. We can vary delta psi independently on boundary, and in the bulk, there is no connection. I mean, we should assume. Do you understand what I'm doing? So now we replace A to A plus delta A. So A is here and there, because B is nabla, vector product nabla and A. So let's start with the first term, namely 1 over 4m minus IH nabla minus 2E over C A plus delta A psi times IH nabla minus 2E over C A plus delta A psi. Psi star. Okay? So, first of all, if delta A is 0, we do have 1 over 4m minus IH nabla minus 2E over C A psi modulus square. So we need to collect now the terms which are proportional to delta A. Okay, so if we take delta A here, so it would be 1 over 4m minus 2E over C delta A psi times IH nabla minus 2E over C A psi star plus 1 over 4m minus IH nabla minus 2e over c a psi times minus 2e over c delta a psi star. So we'll forget about this term because, so I will therefore put arrow. Let me collect the term in front of the gradient and then the term in front of A. So first of all, there is a term 1 over 4m minus IH 2e over c, and here I have psi gradient psi star, yes, with a sign plus, minus psi star gradient psi and times delta A. And you see that this is a paramagnetic part of the current, which we considered before. And the rest is plus 1 over 4m 2e over c squared then it's A, then it's psi modulus square, and also delta A. Okay, with this term, everything is okay. Let me see that I didn't do any mistake. I did mistake. This term comes twice. It appears from here and it appears from there. Okay? Good. So far so good. Now we need to massage the second term and the last one. So I will keep this line intact. Okay? This one. And erase everything else because I need some space. I have a term b square over 8 pi, which is nabla times a square over 8 pi. So therefore it is nabla times a plus delta a times nabla times a plus delta a over 8 pi. So this is again nabla times a square over 8 pi plus I have a twice term nabla a times nabla delta a. So this is 1 over 4 pi nabla times a scalar product nabla times delta a. And I need to do the same trick. I need to transfer the volume integral to the surface integral using Gauss theorem. But before doing that, I also need to massage this term a little bit. So therefore, I will prove here some important identity, which is needed to me. Yeah. I will need to compute the divergence over two vectors C, vector product of two vectors C and B. Okay? Why do I need to do this? Because I will say that C is delta A, this is C, and B is okay? So, I apply the same way of computing this as I used in the previous lecture. So this is divergence. I use Einstein notations, d over dx alpha. Okay? So this is a vector product. I need to take alpha component of this vector product, alpha, beta, gamma, C, beta, B, gamma. So this is what is written on the first line. Okay? Please tell me if you don't understand what I'm doing, you should stop. And if you are not familiar with this technique, you should just make 100 exercises and you will be familiar with this. There is no any other way. So, I have a product of two functions. The derivative of a product is equal to sum of two derivatives. So, this is epsilon alpha beta gamma d over dx alpha C beta times B gamma plus epsilon alpha beta gamma C beta d over dx alpha B gamma. So this is the derivative of product. Now I use the property of Levi-Civita tensors that I can cyclically permute the index. So in the first term I will write B gamma times epsilon gamma alpha beta d over dx alpha times C beta. This is the first term. I do cyclic permutation, I put index gamma in front. In the second term, in addition to cyclic, I should interchange these two indexes. By interchanging these two indexes, I need to replace the tensor Levi-Civita to its minus tensor, because I do non-cyclic permutation. So this is minus C beta times epsilon beta alpha gamma d or dx alpha b gamma. So this is a scalar product B times nabla applied to C minus scalar product C times nabla applied to B. So this is identity which I needed. Okay? So I'm writing down the integral over dr of this term. 1 over 4 pi nabla times A nabla times delta A. So you see that this is B, this is nabla C. So B times nabla C is equal to nabla C cross B plus C nabla B. So this is then 1 over 4 pi integral over dr nabla applied to C is nabla A times nabla A plus 1 over 4 pi integral over dr. Now I have to write C, which is delta A times nabla times nabla times. Okay. This is the surface term. I will use the same Gauss theorem and convert it to the term on the boundary, on the surface. So this is a volume integral, and I will convert it to the term on the boundary. On the boundary, magnetic field should be continuous. Therefore, for any variation of delta A, it should be equal to 0. Clear? Therefore, there is no any boundary condition for that. It is 0 automatically because of continuity of magnetic field. What remains is this term. We computed last time vector product of nabla times vector product of nabla and A, and using the gauge divergence A is equal to 0, we got that this is minus Laplacian. Okay? So therefore, now I combine these two terms and I get the following. I probably do not need the free energy anymore. So, I have equation that Laplacian A is equal to I will permute, well, I will write it down as 1 over 4m IH 2e over c. Here I will write psi star gradient psi minus psi gradient psi star first, plus 1 over 2m 2e over c square psi modulus square a. So what is this? This is 2 mc e. So this is I e over 2 mc. And this is 4e square divided by m. So this coefficient is 4e square over 2 mc square. Therefore, this is 2. E square over mc square psi modulus square a. This is so-called diamagnetic term. Yeah. Okay. This is the second Ginzburg-Landau equation. So let us be sure that we are all familiar with this equation. Namely, we recall the Meissner effect, and we will see that this equation with a minus superconducting current written on the right hand side gives us the London equation. Don't forget that divergence of A is equal to 0. Of course, our equations are gauge invariant. We just used this gauge in order to simplify our calculations. The answer, as we discussed last time, is gauge invariant. Okay, let me then erase everything except two equations. And what we do next, we rediscuss the Meissner effect. We write down these equations in dimensionless form, introduce two length scales, which are penetration depths, which will originate from second Ginzburg-Landau equation. So this is first, and this is second, and discuss the consequences. Okay. Yeah, we should remember that the Maxwell equation tells us that nabla B is 4 pi over C GS, and divergence of B is equal to 0 because there are no magnetic charges. So, this Laplacian A, we said that this is minus nabla times A, and since nabla A is B, this is minus, so, oh, I forgot this 4 pi over C, just, yeah, of course I did it, because this 4 pi, yeah, sorry, this 4 pi, which originated from these calculations, is there, and the power of C comes because I have C there. What I'm saying is that I computed 1 over 4 pi nabla A, nabla delta A, volume integral over d. Therefore, I will write down it as this 4 pi. I will write down C here, and I will eliminate MC in order to make a connection with current. Okay? Good. And this is precisely 4 pi over C, which I needed. So this is minus times B, and therefore it should be equal to minus 4 pi over C GS. So then the superconducting supercurrent GS is equal to I H bar E over 2m psi star minus psi star nabla psi minus 2e squared over mc psi modulus squared. Okay, this is precisely the equation for supercurrent, which we derived on the previous lecture using different arguments. Now we derive this equation from the Ginzburg-Landau equation. And then, if we proceed the very same way, namely, we apply nabla to the Maxwell equation, namely nabla times B is equal to 4 pi over C nabla times GS. GS contains the term with a gradient of phase which can be dropped because the nabla applied as a vector product to the gradient gives you 0, and nabla applied to A will give us magnetic field. Therefore, we arrived to equation nabla beam minus 1 over lambda square beam is equal to 0. So this is the equation which explained the Meissner effect, where lambda 1 over lambda square was equal to eight pi e square over mc square, and instead of psi modulus square we plug in the uniform solution, which is modulus A over B. This is psi modulus square. Okay, so lambda, as we discussed, is a penetration depth. This is how far your magnetic field penetrates into the superconductor. We remember that A depends on tau, therefore if temperature approaches the critical temperature, 1 over lambda square goes to 0, which means penetration depth diverges. This is what we also said is experimental observation. So the London equation doesn't tell us anything about behavior of penetration depths. From Ginzburg-Landau equation, because we have it inside, we have the first equation, we see that the penetration depth diverges. So lambda square diverges at t goes to tc as 1 over stc t minus tc modulus. So lambda diverges as a square root. Okay? Now let's take these two equations, namely this one and this one, and write it down in terms of dimensionless variables. In particular, I will take the first equation first. This one. So what kind of dimensional variables I would like to introduce? I would like to use a dimensionless wave function. By the way, you remember that the wave function psi, as we said, this is square root over ns, the number of superconducting, the concentration of superconducting pairs, I some phase. Let me denote it by phi at this very moment. So dimensions of psi is 1 over square root of volume. Dimension of psi square is 1 over volume. We have our Ginzburg-Landau notion. So we have a term, for example, B psi modulus square times B psi modulus square square, and integration over R. Integration over R gives you volume. So we have a B times volume times psi to the fourth. Psi to the fourth is 1 over volume square. So we have a B divided by volume, and this is dimension of energy. Therefore, B has a dimension of energy multiplied by volume. When we come to some dimensionless variables, you can easily check that dimension of our variables is correct. And the same with A. So I will introduce new dimensionless variable. So I will write that psi, which comes here and there, is new dimensionless function A times, I would like to use the Landau solution, namely square root over modulus A over B. And now I will write down both equations in terms of new function chi. So we have A and actually minus modulus A if I'm below TC and I'm interested in non-trivial solution times modulus A over B to the power 1/2 chi. This is the first term. Plus B psi modulus square is chi square, chi modulus square, chi is also complex function. Then I have modulus A over B times modulus A over B to the power 1/2 chi. And here I have minus h square over 4m nabla minus plus 2e over hca and modulus A over B to the power 1/2 chi. So this is A 3/2 over B, this is A 3/2 over B, and this is A 1/2 over square root of B. So if I cancel out these coefficients here, then what I have is 1 over modulus A square, and I can divide, I can cancel. This is equal to 0. So the equation which I have reads minus chi plus chi modulus square chi minus h square over 4m modulus A square, sorry, modulus A, no, it's modulus A, not square, because I had square root of A over B and I divided by square root of A over B divided by A. So this is A to the first power, modulus A, and I have this nabla, plus I subtract minus A, subtract minus, so there should be minus I to E over HC A square chi is equal to 0. So chi is dimensionless variable. So nabla square has a dimension 1 over x square, right? So this variable should have a dimension of square of the length from the dimensionless analysis, right? What I'm saying is nabla square is 1 over n square, because this is d over dx. Therefore, since this is dimensionless, this is dimensionless, this is dimensionless, this has dimension 1 over L square, this multiplier h square over 2 or 4 m modulus A, this is square of some length, right? I will call it psi. Besides, since A is proportional to tau, this square of length also diverges if temperature approaches to the critical temperature. Okay? The very same way as lambda. So lambda is proportional, inversely proportional to A and psi. Lambda square is inversely proportional to A and psi square is inversely proportional to A. Therefore, their ratio will be independent on vicinity of temperature and critical temperature. Will be independent on temperature, so to say. So let me argue, so let me finish first of all with these dimensionless equations. I will rewrite it now here. The first Ginzburg-Landau equation in the following form. So this is minus chi plus chi modulus square chi plus, let me write it, psi square minus I nabla, h nabla minus I nabla minus 2e over hc a square chi is equal to 0. So the boundary condition will be just replacement psi over chi. So this is the first Ginzburg-Landau equation. Let's do the same for the second Ginzburg-Landau equation. So Laplacian of A is equal to 4 pi over c I h bar e over 2m. I have modulus A over B here, chi star nabla chi minus chi nabla chi star plus 2e square over mc modulus over B chi square A. Again, I can take this penetration depth. Let me do it that way. So it's 8, sorry. There should be, I should multiply it by 4 pi. So this is 4 pi times 2, this is 8. So I would like to transfer it in a little bit different form. So the first term is I8 2 pi e over mcb a. So this is this coefficient. This times this. What it is? Let me write it this way. First of all, I will take the penetration length. So I will write it that this is I 4 pi e square a over m c square b. Since I multiply it and I need to divide by e, I should still have h, I should multiply by c, and I should have a coefficient 1 over 4, and I will write it 1 over 4 pi and add pi here. So this is what? This is I divided by lambda square multiplied by something which is called flux quantum. So this is phi naught divided by 4 pi. So this is the first coefficient. So phi naught, we discussed it when we discussed the circulation in the Bose case, in the Bose superfluid. This is quantum of flux pi hc over E. The same way, the second term is just one over lambda square, right? So therefore, the second equation reads as follows: Laplacian A is equal to I phi naught over 4 pi 1 over lambda square chi star Laplacian chi minus chi Laplacian chi star plus chi modulus square over lambda square. So these are two Ginzburg-Landau equations written in the dimensionless variables. So now, let me for the moment clarify the meaning of this psi. What it is. For this reason, I don't need this, I don't need that anymore. Let me assume that I'm dealing with almost uniform superconductor in the absence of magnetic field. So I will forget about second equation. Let me do some exercise. The first step, I assume that A is 0. I don't care about the second equation. Then I will say that the wave function of my condensate varies very slowly. So the uniform solution chi naught satisfies condition chi naught is equal to 1. Because I drop the gradient, I drop the term with A, and chi naught satisfies this equation. So the equation which I'm going to solve is minus chi plus chi modulus square chi, the nonlinear equation, minus psi square Laplacian chi is equal to 0. So this is the equation. As I said, I assume that my solution is very slowly varying. So therefore, I will say that chi is equal to chi naught plus delta chi. So chi square Laplacian over delta chi is equal to 1 minus modulus chi square times chi. So, and I should still plug it in. And chi naught, as I said, is equal to 1, which means that chi naught is equal to chi naught star is equal to 1. So chi plus delta chi, so chi modulus square is equal to chi naught star chi naught plus delta chi. So it's equal to 1 plus chi naught star 1 delta chi. So therefore here I should put chi naught, and here I already have delta chi. So therefore I have equation which says that psi square Laplace delta chi is equal to delta chi. This is a function of r. This is a function of r. Okay? This equation has very simple solution. This is a Poisson equation which says that the delta chi r depends on r is 1 over r minus r over psi. We discussed the very same equation we discussed Coulomb problem. Which means that the psi, which is h squared over 4ma, has a meaning of correlation length or coherence length. Okay?
Sorry, is there a minus in psi? When you plug, you just use the modulus of psi squared and you put it in the equation.
I said that I open the bracket. Psi modulus square psi naught is 1.
Yeah.
Then there is a psi naught star times delta chi. Psi naught star is also 1.
Yes.
So this is 1 plus delta
So
chi.
when I put it in the equation that I want to solve, so 1 and 1 cancel.
Yeah,
There's
yeah,
minus
just-
psi. So in the final answer shouldn't be a
Yeah, but I forgot. I forgot to write a minus. So when so there is also
Okay.
overall minus here, because I will take it out, and this is minus chi. You see? Thank you. So the equation is of course correct. Otherwise we will get oscillations. You see that. So I put it in the right hand side. So this is psi Laplacian delta chi, and then this is minus chi. So the all sign is minus. Thank you. Good. So let me do the last thing. This is inversely proportional to tau. So I will define psi square as psi naught square times Tc T minus Tc. I will define lambda square as lambda naught square times the same Tc T minus Tc. And I assume that is much smaller than 1. As I said, the ratio of these two lengths, one is penetration depth, another one is correlation length, doesn't depend on T and Tc. Therefore, I can introduce the dimensionless parameter kappa, which is lambda over psi. At the same time, this is lambda naught divided by psi naught. This is so-called Ginzburg-Landau parameter. If I plug in the values of lambda and psi, what I will get, that this is mc divided by e h bar square root over b over 2 pi. This Ginzburg-Landau parameter plays very important role. You can also check that this is dimensionless. As I said, B has a dimension of the energy times volume. If you plug it in, of course it's dimensionless from these notations immediately, but you can also check that this is dimensionless, and we did not make any mistake. We discussed it on the very last lecture about superconductivity, that this Ginzburg-Landau parameter actually determines whether you are in so-called type 1 or type 2 superconductors. But for doing that, we need to analyze the Ginzburg-Landau equation and find so-called vertex solution in a magnetic field. This is what it was derived for. Again, Abrikosov got a Nobel Prize in 2003 together with Ginzburg and Leggett for prediction of the vertex lattice, which has enormous significance for technologies, tomography, yeah. And we will see that the criterion written in terms of dimensionless parameter kappa determine us whether we have type 1 or type 2 superconductor. Just for those who would read the literature, the superconductors where psi is much larger than lambda, psi is much larger than lambda, and therefore kappa is much smaller than 1, are called p-part superconductors. This is the p-part limit. And the opposite limit, if the connection length psi is much shorter compared to penetration depth, it's a London limit. So two limits, kappa much larger than 1 London, kappa much smaller than 1 p-part. Okay, that's all for today. Surprisingly, I'm done in 1 hour and a half. Any questions?
Parameter B depends on atomic parameters.
Yeah. B depends. B is a kind of parameter which doesn't depend on temperature, but it depends on material. One can associate it with upper critical field, for example. It's measurable from experiment. Yes. We discussed it again. I will come back to this discussion, how to determine. First of all, on Friday, we will discuss microscopic theory. So this will probably be one of two exceptions. The first one was the weakly non-ideal Bose gas, weakly interacting Bose gas. When we started with Hamiltonian, you see that in most cases, I don't need the Hamiltonian at all. This is why this course is called Phenomenology. But on Friday, based on the Hamiltonian which we derived, namely early Hamiltonian describing electron-phonon interaction, we will proceed with derivation of microscopic equations, which are called Bardeen-Cooper-Schrieffer BCS equations of superconductivity. So we will get all the parameters from there, we will get thermodynamics from there, but the Ginzburg-Landau theory can be derived from the microscopic theory also. We will take Hamiltonian and end up with the same phenomenological equations. This was done by Lev Garykov in 1960, which showed that these two theories match. So one, namely the phenomenological, can be straightforwardly derived from the microscopical one. And then we discuss the experiments which determine the phenomenological parameters. So basically, in the Ginzburg-Landau, we have three coefficients. Well, one we already encoded in the mass. Sometimes for generality, people write coefficient C in front of the gradient term. We put it in the mass. And there are two independent coefficients, A and B, which can be subtracted from two independent experiments. That's it. And this is a property of material, as you correctly said.
In order to reason, in the non-knowledge theory, we run down the function of the free energy, and we minimize it.
Yeah.
And then we get the dynamical equations of the field.
It's not dynamical. We didn't tell anything about time. We are talking about thermodynamic equilibrium. The system is in equilibrium. There is indeed something which people call time-dependent Ginzburg-Landau equation. But this is very subtle thing. In principle, in order to derive time-dependent equations describing dynamic, one needs to write a quantum field theory. One needs to write effective action, which will contain the dynamical term, which is frequency dependent or contains derivative with respect to time, and then some theory can be constructed. But we are dealing with thermodynamics. We are saying that we Taylor expand the thermodynamic potential, or we assume that thermodynamic potential is a function of the parameter, but system is thermalized, it's in a thermal equilibrium, there is no dynamics.
Why you don't include linear terms in the other parameter?
Because we are expanding around minimum. And like with oscillator, when you derive your theory of oscillator, your potential has a minimum and we are expanding around stable minimum. Otherwise you have a force which will actually... Any other questions? Good. There is a little change in schedule, so next week there will be 3 lectures. On the week after the next, on 19th, we will have a lecture. On 21st, we will have a tutorial. And on 23rd, you will have the last lecture, which will be with slides, will be summary of these two topics, namely superconductivity and magnetism, the same way I summarized fermions and bosons in quantum gases with a slide lecture. And we discuss experiments. Good.